guys, today we're talking about hyperbolas. We are continuing on. We are on our third of 4 conic sections that we're going to be studying, and hyperbolas are very, very similar in the way that we construct them to ellipses, but there is a pretty big difference between them. Okay, so really briefly, let's just kind of recap conic sections with circles and ellipses. With circles and ellipses, we have 2 halves of curves that are coming together to make one whole. Now with a hyperbola, we still have 2 halves of a curve, but they are facing directly away from each other. So what you're going to see is that we have the equations for ellipses and for hyperbolas are very, very similar, almost identical in fact, except for one small difference, okay? So it's super easy. If you found ellipses pretty easy, then hyperbolas will be equally easy for you, I think. So here we go. All right, hyperbolas are created by cutting vertically into a cone. Actually, in this case, it's not just one cone, it's 2. So if you have the full hyperbola, you have to have both sides of it, okay? So one up, one down, or one left and one right. It's not one or the other. Okay, so here we go. So let's make a cut vertically into this cone, and what happens is you get a curve just like this, and then the bottom, imagine the bottom of the cone is flat, okay? Same thing on the top. So we have a curve, and then it goes dotted and then flat. Okay, so we end up with this piece up here and the one down on the bottom. And what you see is, if we're going to translate it to the graph on the right hand side, that means we have a curve going upward like this, so this represents the top curve, and then we have a curve going downward, and they mirror one another. Okay, so we're going to learn how to construct these, but just the same as with ellipses, they can be located all over the XY coordinate system. So I'm going to put some key terms on here, and then we'll go down and look at kind of the nitty-gritty details of them. Okay, so what we have is one of the ways that we're going to construct these is by having lines here. So we're creating these X's that go through the center of the ellipse, the center of the hyperbola. So the center of this one, in our kind of arbitrary example, is 0, 0. And we have these diagonals that are cutting through it. Those diagonals have a name, and it's one that we've actually studied before. So it's an asymptote, plural asymptotes. So we have 2 of them here. And remember that hyperbolas, or any asymptotes, what they are they're lines that a graph gets very, very close to but never actually touches. Okay, so we're going to use those to help us guide our how we construct the hyperbola. So this is the center. And then we also have foci for hyperbolas. So the foci are only located on the same axis as where the curves are. Okay? So this one is a focus, and this one is also a focus. And so the distance from, let me go ahead and draw one more thing in here. This distance from the center to the focus is called C again. Just like it was with hyperbolas. With ellipses. Okay, so that's the basics. So now let's go through, again, I want to do a short recap of circles and ellipses, because you're going to see that there is only one small difference between the equations for circles, ellipses, and hyperbolas. More specifically, ellipses and hyperbolas. So the big thing that I have in red here that I really want you to clue into is that with circles and ellipses, they are added together, okay? Again, think 2 halves of the curve coming together and meeting to create one cohesive shape, okay? So, because I have that positive there, I know that you all can probably guess what the one difference is between the equations for circles, ellipses, and then hyperbolas. So, get that guess in your head and see if you're right when we go through here. All right, so now I can take this away. Let me move this up just a little bit to make sure you guys can see it all. Okay, so standard form for an equation for hyperbolas. Center at 0, 0, center at HK. So, center at 0, 0. x squared over a squared minus y squared over b squared equals 1. So that's the big difference, is that we have a minus here instead of a plus. But we also could have y squared over a squared minus x squared over b squared equals 1. So what we saw yesterday in the ellipse is that the a and the b switched. X and y stayed in the same position and a and b flipped. Now it's the opposite. Okay, so the difference between these two is in this one, the x is positive. So what this means is that the curve it opens in the x direction. So x direction or horizontally. This one, the y is positive, so it opens up or down or in the y direction. So opens in the y direction. Okay, sometimes, and actually sometimes you will see that it'll say negative x squared over b squared plus y squared over a squared. So it's not whichever one comes first, it's whichever one is positive. That's the way that the curve opens. And you'll see, again, how we actually construct these shortly. Now, the only difference between center at 0, 0 and center at hk is, you guessed it, the same as in ellipses. We have x minus h squared over a squared minus y minus k squared over b squared equals 1, or, just like we have over here, y minus k squared over a squared minus x minus h squared over b squared equals 1. Okay, so I'm not gonna, because we're gonna run out of space on our next few examples, I'm not gonna actually attach this up at the top. So make sure you guys have this written down and accessible as we move on to our examples. Okay?